continue. We had left off on this slide, which introduces the concept of decomposition reactions. Very generically on the top, a single substance decomposes or produces several substances, at least two, obviously, because you need to make something more than just one thing. Otherwise, it's a different kind of reaction that we're going to see. Here's a real example from a reaction that can happen within your body if you have uncontrolled diabetes or are in a extremely restricted diet of low carbohydrates, these new keto diets that are out there. So you become ketotic and you produce this compound, which is called acetoacetic acid, and then that turns out to decompose to carbon dioxide and acetone. And you can actually smell the acetone in the breath of the person, particularly if it's more common with diabetics that are uncontrolled and they're coming in with all kinds of issues related to their disease. But even in a healthy person who's following a very, very strict ketogenic diet, it's a physiological response, as we're going to see later when we talk about the metabolic pathway that leads to the production of these compounds. But this compound on the left is produced as part of that, and then it spontaneously decomposes, and then acetone is very volatile, and it ends up in your blood and it ends up in your breath, and you can smell it. So we mentioned the hydration and dehydration type reactions, right? So again, I just went back one slide. If you have an alkene and then the components of water, which you can dissect into HOH, oh boy, I'm telling you, can't win, right? Can't win with technology. I know, right? Just kill me with the technology. Let me see if this is going to do it, but I doubt it. Anyway, all right, I'll do it on the board. So remember, H2O, you can dissect it into two components. If you call that the X and this the Y, right? So you've added XY, i.e. HOH, oops, I went forward again, across the double bond, same thing here. So when you have an alcohol in a structure, the reverse process that then releases the XY, i.e. water, is called a dehydration reaction. So the generic pathway shown on the top, which is the loss of that XY pieces that end up getting themselves together and departing, and then leaving an alkene in its place, this is known as an elimination reaction, which is the opposite of addition. But specifically, if water is what's being lost, then we call it a dehydration reaction. And we're going to see many examples of dehydration reactions in biochemistry. For example, here's one. This is one of the later steps on the glycolysis pathway that we're going to be learning later, in which this compound loses water to become this compound on the right, which is called phosphoenolpyruvate, and then water is released in the process. So hydrations and dehydrations are extremely common in biological reactions. Well, everything's happening in an aqueous environment. And there's such a thing that what we call metabolic water, which is water that is produced as these larger entities get broken down into pieces and things happen to the pieces as things happen. And there are many examples of these dehydration reactions. So loss of a small molecule from a larger entity in the grand scheme of things is an elimination reaction. But these are all decomposition processes. One thing making several. Okay? All right, so we talked about single replacement in the context of ballroom dancing. Here's the couple that's dancing. Here's the single person that's kind of cut into the couple, right? And then one of these two ends up with the C, and then the other one ends up by itself, right? So this is very generic up here. But here's, again, another example of an important biological transformation that we're going to talk about a little bit later in more detail. So when you breathe in CO2, the CO2 becomes carbonic acid. We talked about that one as a composition or synthesis reaction. Well, it turns out that bicarbonate doesn't hang around for too long it is in an aqueous environment. It actually interacts with the water that's surrounding it. And then there's a proton transfer. A hydrogen atom is transferred from the carbonic acid to the water to produce this outcome. And if you notice, this one loses one part and it ends up on the other one, right? And then what's left kind of goes away on its own. So if you analyze this reaction, this is a single replacement transformation. Okay? We're going to see later when we get to a couple of chapters from now that this is actually an acid-base reaction as well. We haven't talked about acids and bases, but we will, and I'll give you a little preview. Any substance that in aqueous solution is capable of losing a hydrogen atom in the form of a hydrogen ion, i.e. H+, and transfers that proton, it's technically a proton, to a water molecule to produce this structure, H3O+, this is what defines an acid in an aqueous system. Okay? We're going to get to that in more detail. But as we're going to learn, this specific transformation, as simple as it seems, is critically important in the maintenance of the acid-base balance of your bodily fluids, particularly your blood. And it's a very, very important reaction. So these single replacement reactions in the context of organic materials, because if you realize these compounds, you may argue that they have carbon and they're therefore organic, but it turns out, by definition, all carbonic acid and all of its derivatives, including CO2, are considered inorganic, even though they have carbon. There's only a handful of compounds that can be classified in that way. But if you look in the context of organic compounds, these single replacement transformations are more commonly referred to as substitution reactions. Because if you realize something has substituted on something else by this transfer process of one piece. So here's, again, very generic, but you can sort of observe, if you pay attention to the structure here sort of in the middle, the tetrahedral carbon that has the Y on it, and then the X comes along, a pair of electrons on the X approaches the carbon, and because carbon has a full octet, right, 4 bonds, if you have a pair of electrons that's approaching the carbon, well, something has to go because carbon can't form 5 bonds. So what happens is that the Y falls off together with the pair of electrons that is holding it onto the carbon. And for those of you who are in my organic chemistry course, we're going to see this ad nauseum. This is what we call a leaving group. Anyway, that's for that class. But this attacks carbon, displaces the leaving group. And if you realize there's been a substitution, Y has been substituted for X. Okay? So these are very common reactions. Here's a biological example. So the synthesis of epinephrine, otherwise known as epinephrine? No? Physiology, anatomy? Well, physiology. Nobody knows the alternative name of epinephrine? It's a critically important hormone. It starts with an A. Yes? Adrenaline. It's adrenaline. It's the other name for adrenaline, right? So it turns out that adrenaline or epinephrine, notice there's a methyl group here. Well, it turns out the precursor, the immediate precursor to epinephrine is norepinephrine, also known as noradrenaline, right? There's an amine over here that reacts with this methyl group, so the lone pair on the nitrogen forms a new bond to carbon, and then the sulfur and everything attached to it falls off, becomes that leaving group that I mentioned earlier. But the point is that the nitrogen has now acquired something different, right? And this is a single replacement type reaction, which is, in the context of organic systems, it's referred to as a substitution reaction. Okay? So the next is the double replacement. So again, if you look at the top, they're very generic with the letters A, B, C, D, etc. Again, this is two couples that are dancing and they exchange partners with each other. So AB plus CD, and then notice that A ends up with D and C ends up with B. So they both exchange pieces, right? So if you recognize that, that's what's happening, then this is called a double replacement or a metathesis reaction. So here is, for example, This compound on the left is, anybody recognize this compound? I think we talked about this compound. We did in 5Chem1. So this is aspirin. So when aspirin enters into aqueous systems, you need a little bit of acid to break it up. But anyway, when it reacts with water, what you'll notice is that the hydrolysis reaction takes place. And if you pay close attention, you'll notice that, again, you can dissect water into HOH components, right? The two pieces. And if you observe the structure of the acetylsalicylic acid, and we've highlighted things in color, so it turns out the proton, one of the two protons on the water, the one that's highlighted in blue, ends up on this oxygen that forms the ester in the acetylsalicylic acid, and then the acetyl group that's over here ends up with the OH component of the water. So there's been a swap between the two structures. Okay? So again, recognition of that then would classify this reaction as a double replacement process. So these hydrolysis reactions are very, very common. In fact, everything you put into your mouth that needs to be digested so that it can be absorbed, all that's happening to these compounds, whether they're sugars, they're proteins, they're lipids, or whatever they may be, they're being hydrolyzed, broken down by the actions of enzymes, including water, which recruit water to do the process. And they're being hydrolyzed into smaller pieces. But what's happening is that these reactions in which there's, again, an exchange of the water, pieces of water with pieces of something else, they're all being broken down into smaller components. And this is what's called a hydrolysis reaction. Okay? So here's just a couple of examples of these types of molecules. These are among the most common and important transformations in biochemical systems. And again, by definition, what's happening in these types of processes, at least in biological systems, is that larger molecules are broken down into pieces, smaller fragments, through the actions of water. And again, enzymes are needed in these biological systems because things just don't happen randomly. So here, for example, anybody recognize this type of compound? We're going to be learning this in detail in this course, but just in case anybody has seen this before. This little thing that looks like two identical pieces linked together. So this is the general structure of a sugar, of a carbohydrate. Okay? This happens to be a disaccharide. There's two sugars, right? All of this is going to be, at the end of this course, all of this will be part of your normal vocabulary. So just FYI. So anyway, if you observe, here we actually didn't color-code it on this side. Well, actually it wasn't necessary because it's the water that splits between the two. So it is correctly color-coded. So notice the HOH, and then you have these two pieces. Well, one of them ends up with the OH, the other one ends up with the H, right? And then the oxygen that's in the middle here that doesn't have a color is this one that's attached to the hydrogen, it turns out. So again, this is a hydrolysis reaction, which is technically a double replacement process. This here is what we call a peptide, a dipeptide. This is a building block that makes up proteins. Okay, we're going to talk about proteins later, another class of biological structures. So if you observe again, now here we're highlighting something that you've still not learned of, which is again acids and bases. But the point is that initially the OH in red ends up here, and the H in blue ends up here. But as we're going to learn, amines are basic compounds. They pick up protons from acids. So what would have been a carboxylic acid over here, that proton is actually ultimately donated to the amine. But the point is that this bond, well, this bond here, and unfortunately my pen isn't working, but the bond in which you have the nitrogen to the carbonyl, that's the one that's broken down. And then initially what forms is a carboxylic acid, and then you have the amine. There's another lone pair on the amine as well, right? And it's this lone pair that ends up picking up that proton. Okay? That's why you end up ultimately with this structure on the right. The point is that the water is broken into two pieces. The other compound, whatever it may be, small, large, complex, simple, is also broken into two pieces, and then pieces are exchanged between the original compounds to produce the final product, right? And because it involves water, and the water is broken up, and the other compound is broken up, and the components of the water end up distributed between the two, this is a hydrolysis reaction. Yes?
In the first reaction,
Yep.
are the two products the same molecule?
They end up being the same molecule,
And
yes.
So that can be the case?
Yep. This is, if you follow good observation, this is a very critical observation because, again, part of the, as you're going to learn later when we get to these types of compounds, you have to pay very close attention to detail as to the relative positions of all of these OH groups. And if you follow down, down, up, down, 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 up, down, these are identical products. Yeah, you end up with two of the same. But in some cases, the left side and the right side of the one on the left is not the same, so when they break up, you end up with two different compounds. We're going to see this later when we talk about glucose and galactose and different things. All right. And then the last category would be the rearrangement or isomerization, and this is when a single compound changes its organization of its atoms, which we call a rearrangement or isomerization, and then you end up with a different structure with exactly the same composition. So formula is the same, but there is a change in how things are arranged. Now, we've already talked about constitutional isomerism, in which the compounds have different connectivity. This is what's illustrated here. We're going to be learning later on in the course an alternative type of isomers, which turn out to have exactly the same connectivity. What changes is the relative three-dimensional orientation of the pieces in space. That's a more refined level of difference. We're going to talk about that because it turns out to be exceedingly critical in biological systems. But here, we're talking about a constitutional isomerization. Notice the phosphate is on carbon number 3. This is called 3-phosphoglycerate. And then in the product, it ends up on the second carbon, which is 2-phosphoglycerate. This is one of the steps in glycolysis as well. There needs to be an isomerization for that compound to be able to do what it needs to do. So we're going to see examples of this. All right, everybody's with me? We're on channel 70 as usual. So, you're going to do an exercise in the lab, not next week, but the week after. The reason why we have this lag, and we started on week 1, and then we're going to have no labs on week 2, is because we want this lecture to be ahead, to ensure that you see the concepts here first, and then lab is just reinforcement, as opposed to seeing something for the first time, right? We always attempt to do that, but sometimes we can't. Things don't work out, and then, of course, if Mother Nature decides to intervene, then good luck, right? But anyway, hopefully things will work out. No snow in the forecast for next week, right? No? Okay. All right, so you're going to do examples of a lot of these things, and you're going to actually do some hands-on observations of specific reactions. So, thus far, we've been talking about classification in terms of how the atoms are arranged relative to each other, pieces of structures changing places, and things of the sort. Turns out there's an alternative and not mutually exclusive, so you can follow both things, both concepts simultaneously, and in fact you should. Because it turns out we can also classify reactions on whether there's been an exchange of electrons between the species that are reacting. And in that situation, then we classify the reaction as being a redox reaction. If that does not happen, then we call it a non-redox reaction. Okay? So, turns out that when you're looking at the different elements interacting with each other, regardless of how large or small the difference of electronegativity is between two atoms, whenever you have two different atoms coming from two different elements bonded to each other, regardless of how small the difference in electronegativity may be, as long as there is a difference in electronegativity, that will result in, as minor as it may be, a reorganization of the electrons between the atoms as they're bonding. Only when the two elements are identical, the two atoms that are bonding are identical, we're talking about then atoms of the same element, that's when there's absolutely zero reorganization, right? Because you're talking about exactly the same electronegativity, and there's no unequal distribution. So what that then leads to, it turns out, to simplify why we're mentioning this, is because what you need to then realize is that any reaction that consumes and or produces a pure element must be a redox reaction. Because if you don't start with pure elements, that means that the different atoms coming from the different elements that are bonded, their electrons are reorganized in a certain way. When a pure element forms, those atoms that are exactly the same come together. The organization of electrons in that situation is different than what it was in the original reactants. So the bottom line, don't try to give it too much thought, right? Because it's probably beyond what you would need to know. But the bottom line that what I want you to understand is that one way to identify redox reactions is if you observe that there's a pure element at the beginning and or at the end that wasn't there before. Okay? So anytime a pure element is consumed and or produced in a chemical transformation, by default, that reaction must be a redox reaction. So we can actually quantify, this is the way to do it just by observing. If you see pure element, there's one way to do it qualitatively. So you just kind of, you observe, I see pure element, this has to be redox. But there's actually a way to put a number to it, to quantify it. And it turns out that there's this concept which is like an electrons bookkeeping system that allows us to establish whether there's been a electron redistribution or reorganization, i.e. a redox process. We call that the oxidation state or oxidation number. So it's a number that you assign to an atom of an element, and you do that for every atom of every element in a compound to establish how that element and the electron count that is carrying differs from the elemental state. Okay? And if there's a change of oxidation state from the pure element, which by definition has an oxidation state of 0, to something different than 0, then what you then can establish is that that element has been engaging or has involved itself in a redox transformation. So the oxidation state or oxidation number, those two things are synonymous. By definition, is the charge the atom of the element would have in the compound if, this is a big if, it's just a convention to assign these values, if all of the bonding electrons entirely belonged to the most electronegative element in the bond. Okay? So for pure elements, because there's no difference in electronegativity between the atoms that are bonded, then the electrons are equally distributed, you end up with an oxidation number of 0. But when they're not bonded to themselves, they're bonded to other things, and you then distribute the electrons in such a way that the most electronegative element is assigned all of the electrons in the bond just for the sake of bookkeeping, then that's going to result in the more electronegative element having a more negative oxidation state, and the less electronegative element having a more positive oxidation state. Therefore, since they no longer have a zero oxidation state, then there's been a redox reaction between those elements. Okay? All right. So this is what I've just said, right? The more electronegative element will have the smaller or more negative or less positive, however you want to look at it, oxidation state. The less electronegative element will have the higher, meaning more positive or less negative oxidation state. Now, it's important to understand that these numbers that we're going to start assigning to things, they're not a true reflection of charges or electron distributions. They simply allow us to determine when elements are bonded to each other than to themselves, which one is tending to be the more electron-rich, meaning taking or attracting electrons more toward itself, and then the one that's less electronegative will have less. So one's going to be more electron-rich, the other one's going to be more electron-deficient. Now, if you remember, this definition sort of resembles, but in a very, there's a major difference, resembles the definition of formal charge, if you remember when we were doing Lewis structures and assigning formal charges. How do you determine formal charge on a Lewis structure? Anybody remember that? Yes?
How many electrons there are and subtract from the number of electron efficiency.
But if you're going to use a sort of a sentence like that one, what's going to be the difference? So charge the atom would have if all of the bonding electrons, and that's where it changes, were or are assumed to be equally distributed between the bonded atoms. So you split them equally. That allows you to determine formal charge. If you give them entirely to the most electronegative element, the number you're going to get is the oxidation state. So it's the calculation at the end turns out to be the same. You're simply subtracting from what the atom ends up with from what it has as an element. That difference, if you've split them equally, the number you get is the formal charge. If you give them all to the most electronegative element, what you get is the oxidation state. Okay? All right, you're going to see how this works in a moment. All right, so there's a series of rules or guidelines that you need to be aware of when you are assigning oxidation states. The reason why we need to talk about all of this is because when you're looking at structures, molecules, compounds, substances in biological systems, first of all, the state of oxidation of different compounds is important in how the body perceives them, utilizes them, what happens to them, how they act. And as we're going to learn, oxidation reduction reactions are amongst the most important types of transformations that happen in biochemistry. So you need to understand these concepts. They're very, very critically important that you do. So we're going to start simple. When you're looking at simple ionic compounds, binary compounds, a metal and a nonmetal, the metal, of course, is the cation. The nonmetal is the anion. So the oxidation state is simply the charge on the ion. So, of course, elemental potassium has an oxidation state of 0, because all elements have an oxidation state of 0 because nothing has happened to them, right? But when and so does bromine, right? But when potassium and bromine react and you form KBr, potassium is a group 1 metal, loses an electron, gives it to bromine. Bromine is a group 7 nonmetal, becomes bromide by gaining an electron. We already knew that, right? So if you look at potassium, the charge on the ion is +1, so its oxidation state is +1. So compared to 0, which was elemental potassium, it has become a higher number, more positive, right? So potassium is in an oxidized state relative to the element, because it's K+. Bromide has a charge of -1. Its oxidation state is -1. So relative to elemental bromine, which has an oxidation state of 0, this is more negative, right? So this is in a reduced state. Remember, oxidation means loss of electrons, right? You become more positive. Reduction is gain of electrons. You become more negative. And then you can now tie that together with states of oxidation. Any atom that has lost electrons and has gained positivity, it has become oxidized. Its oxidation state is reflective of its charge. Okay? If the converse is gain of electrons where they have become reduced, we still call it oxidation state. Technically they're reduced, but their oxidation state is a negative number, because that means that they're actually in a reduced state. But to avoid confusion, the convention is to simply speak of oxidation state or oxidation number. If it's positive, the substance exists or the atom exists in an oxidized state. If it's a negative number, then it exists in a reduced state. That's why its oxidation number is negative. Okay? So here's magnesium chloride. If you dissect this, this is magnesium 2+, and there's 2 because the valid charges have to be balanced, right? There's 2 chlorides. So magnesium ion is 2+ charge. Its oxidation state is +2. The chloride ion charge is -1. Oxidation state is -1. So typically, when we're talking about this, again, the oxidation state of the most electronegative element, right? In this case, chlorine and bromine, it's going to follow the group number that they're in, right? Based on the charge that the ions would acquire based on the group that they're in. We've already learned these concepts in the previous half of the course. And again, the less electronegative element would simply be the positive counterpart based on what the more electronegative element is. So we're going to see what happens with molecules. This is talking about molecules. So when you're talking about molecules, you assign first to the most electronegative element the charge it would have if it were an ion based on its group. That's what this is saying. And then the less electronegative element, you have to do a little bit of a calculation to determine what its charge is based on the net or total charge of the molecule. Let's look at examples so that you can see. That's coming up in a moment. Did I go back to forward? Hold on. Oh, all right. So this is what I already said. When you're looking at a chemical transformation, because for a pure element that has become part of a compound, its oxidation state necessarily has to change from 0 to whatever it ends up being. Those reactions that involve pure elements are necessarily redox. What this is saying is that when you're making calculations of oxidation states or numbers of elements in a reaction, there may not necessarily be pure elements gained, consumed and or produced. But if you observe a change in the oxidation state or oxidation number of any element, that reaction has to be a redox process. Because any change in oxidation state implies that there's been some kind of exchange of electrons. Okay? So what this then means is that if you simply observe that for one element, there's been a change in an oxidation state, well, what does that mean? That means that a second element must have changed as well. And continuing with that, one had an oxidation state that went up, it became oxidized. Well, what that means is that the other element whose number changed, it must have gone down and become reduced. Because as we've already established, redox reactions must go together. You cannot have an oxidation in the absence of a reduction. So if you identify something having become oxidized by its oxidation state or number going up, then you need to go fishing to see which one got reduced, because there has to be something whose oxidation state went down that then got reduced. And then the last thing you need to be aware of is that ultimately, because electrons cannot just come or go from nowhere, the total number of electrons lost via oxidation must match the total number of electrons gained by reduction. There has to be a perfect equitability of the charges before and after the reaction. So, let's look at some examples so that you can start looking at things and identifying. And because my pen is not working, I'm going to have to do this on the board. Let me try again, but I have a feeling this is futile. All right, looking at the first reaction. Do we have an eraser? We do. Is that reaction redox, yes or no? How do I know? Because there's pure elements. In fact, the two reactants are pure elements, right? And they've both been consumed. So we have S plus Cl2 making SCl2, right? So oxidation state on sulfur on the left. Zero. It's a pure element. Oxidation state on chlorine on the left, 0. Now the question is, what's the oxidation state of sulfur on this compound? Well, now is when you have to, that was that slide that I perhaps was a little confusing, this one here, that talks about this part, about molecules, right? This is what I'm going to dissect now. So here, the first thing you do is you identify, for binary molecules, right, two elements forming a molecule, right? If you draw the Lewis structure of this thing, it's like this, right? So this is a binary molecule. Yes? So, I'm going to leave this here for a moment for a reason. So, but if you, never mind this, so binary compound, binary molecule, which one is more electronegative, sulfur or chlorine? Chlorine is more electronegative. So then you assign to the more electronegative element the charge it would have based on its group if it were ionic. So that would be for chlorine, this is group. Group 17 or 7, right? So the charge it would acquire, it only needs how many electrons to become, to reach 1, right? So this would then be -1 on chlorine. So now we need to figure out what the oxidation state of sulfur is. So the sum of all of the oxidation states has to equal the net charge on the entire structure, right? The charge on the structure is 0, right? So that means that sulfur plus 2 times -1, because there's 2 chlorines, each one is -1. This has to equal the net charge on this structure, which is 0. This is as much math as we're doing in this course, right? Well, no, actually, we're going to get more math later in this section of the course. Let's put it that way. So then, if you solve for sulfur, sulfur is 2 plus or plus 2, right? So then the oxidation state of sulfur is +2. Okay? So in this process, because chlorine is more electronegative than sulfur, the electrons in each of these sulfur-chlorine bonds are sort of attracted towards the chlorine more than they are towards the sulfur, right? So that's why then we say sulfur has become oxidized, because it's technically losing electrons towards the chlorine. The chlorine is the one that becomes reduced because it's attracting those electrons. Now, in reality, we don't have any ions. There's no charge. This is just sort of a count to assess what happens. So then what we can establish is that the sulfur, this is the oxidation reaction, and then the chlorine is, this becomes reduced, right? This is the reduction. Yes? Now there's an alternative way of doing it that is covered in your textbook. I'll introduce it briefly. So the alternative way requires you to draw the Lewis structure. If it's simple like this, it's not a big deal. If it's some complicated monstrosity of the molecule, then forget it, right? But for simple things, you can draw the Lewis structure, and then we rely on the definition that we've established for oxidation state, which says the charge the atom would have if all of the bonding electrons fully belong to the more electronegative element. So if I look at my Lewis structure and I assign the electrons to give them, and all of the bonding electrons entirely given to the most electronegative element, right? And then I do my comparison. So chlorine, how many electrons does it start with as an element? Well, it starts with 7 because it's group 17. How many does it end up with by this assignment of giving all the bonding electrons to the more electronegative, i.e. chlorine? So 2, 4, 6, 8. So you subtract 7 minus 8, you end up with minus 1. Same thing happens with the other one because it's the same. If you look at sulfur, sulfur starts with 6 because it's group 16. Subtract how many it ends up with. Well, these belong to chlorine, right? It only has 4. Then you end up with plus 2. Okay? It's very easy to do it that way. So if you can put together the Lewis structure correctly with all of the lone pairs and all of the bonds in the right places, all you need to do is assign the electrons to the more electronegative elements in the bonds, and then just do your count. What did it start with? What did it end up with? That difference tells you, the damn thing is in my way. Put it over here, right? You can see it, right? End up with a minus 1. 6 minus 4, oxidation state is plus 2. Okay, everybody's with me? All right, so the first one is a redox process. What about the second one? Well, you don't see any pure elements. Doesn't necessarily mean that it's not redox. But in the grand scheme, so first of all, let's put it together with the first discussion. In the other classification, the first reaction is what kind? Synthesis. Right? Two things make one. This is a synthesis or combination or composition reaction. The second one is in the previous classification, and if you draw water as HOH, then you'll see it more clearly. It's a double replacement process, right? So it turns out that double replacement reactions, and I can't think of any, Dr. Geiger has sat down and tried to figure out, is there any example that it's not the case? We don't know if there is, we don't think. Double replacement reactions are by default non-redox. Unless somebody finds one, but we can't think of one. Anyway. So you can dissect it, right? So if you look at that reaction and you dissect the different structures, you have sodium plus, hydroxide is like this. Okay, this is formal charge, not oxidation state. And then that reacts with HCl, which is like this, right? And then ultimately that produces NaCl, which is this plus this, and then it produces HOH, right? Yes? All right, so the oxidation state of sodium does not change because it's Na plus and it's Na plus, so nothing has happened with sodium. Hydrogen, this is now a molecule, so then you need to go by the rules that we discussed. The more electronegative element is oxygen. Yes? Based on group 6 that it is, its oxidation state would be -2. Yes? And for the charge of the whole thing to be -1, the charge on hydrogen, the oxidation state of hydrogen has to be +1. Right? So this is +1 and this is -2. Those are the oxidation states. Everybody sees that? HCl, and you can also go by the alternative way that I just showed you. Let's do it up here so that you can see it. More electronegative is oxygen, right? You give the electrons all to oxygen. Proton starts with 1, ends up with 0, so +1, right? +1 oxidation state. Oxygen starts with 6, right? Ends up with 1, 2, 3, 4, 2, 4, 6, 8. -2 oxidation state. So this will never fail. Never fail. Okay? All right, just FYI, I'll leave it there. All right, so then this one. Again, more electronegative is chlorine. So group 17, this is -1. For this whole thing to have no charge, this has to be +1. Yes?
Can you write on the slides?
I can't. This is my problem, that my pen is not working, unfortunately. I typically do, and it says here, reboot computer if pen is not working. Well, before even doing anything, I rebooted the computer, right? And it's not working. So unfortunately, I don't want to reboot it again because then it's a major issue. So I'll have to call IT to ensure that they come back and make sure that this is operational. So +1, -1. So again, hydrogen here is +1, the same as here, and the chlorine is -1. What happens down here to the chlorine? It was -1 up here, and it's -1 down here. So that didn't change. And then if you go to H2O, right? Oxygen is group 16. Oxidation state would be -2 because it's more electronegative. For the whole thing to have a charge of 0, which is H2O, this has to be +1 and this has to be +1. Yes? You can also do it by the alternative system, assign the electrons to the more electronegative element, oxygen, right? So the hydrogens end up with 1 minus 0 is +1, 1 minus 0 is +1, and then oxygen, 6 minus 8 is -2. So again, oxygen was -2, it's -2. Hydrogen, they were both +1, they're both +1. There's no change in oxidation state of any element in this transformation, so this is not redox. All you can say is double replacement, and then add the non-redox reaction as the tag. Yes? Everybody's with me? Yes, sir.
Is hydrogen always going to be +1? Or
Typically, it is when it's bonded to a more electronegative element. There are situations in which it can be -1. So, for example, if you have this compound called sodium hydride, so in this case, you have Na+, and then it turns out this is the charge. But if you compare this, in this case, hydrogen is more electronegative than sodium. So if you do the math, it ends up being -1 oxidation state. But for the most part, it's going to be +1, with some exceptions. Yes?
I don't want to interrupt you, but is the L light turn on around there? Because
I can. Yeah, if you want to do that, I can do.
It makes it a lot better.
Sure. Sorry.
Thank you.
Yep. All right. Hopefully that helps. She's taking a photo. All right. So, the third reaction, redox. Yes, sulfur pure element, hydrogen pure element, making a compound, right? What's the oxidation state of sulfur in the product? So it's going to be 0 for on the left for both because they're elements. What's the oxidation state on the right? So in this case, it's -2. So in the first compound, it was +2 because chlorine was more electronegative than sulfur. In this case, because sulfur is more electronegative than hydrogen, it is assigned a -2 oxidation state, and then hydrogen ends up being +1. Okay? All right, is that fourth reaction redox? Yes, question? Yes. Say again? The name, well, it's a redox reaction, and it also turns out, just like the first one, it's a synthesis or composition, because two things make one. All right, so again, if you want me to just dissect it here, right, I can do that. So S plus H2 makes H2S, right? So 0, 0, and then this one ends up being +2, and this ends up being, -2, and this ends up being +1. Again, if you do the alternative method that I showed you, similar to H2O, right? You give everything to sulfur, this ends up with +1, and this ends up as a -2 oxidation state. Yes? What about the fourth one? So we know it's redox because We have a pure element at the beginning, which is bromine. We have a pure element on the right, which is iodine, elemental iodine. So the question is, what was reduced and what was oxidized? Because this is another thing you need to be able to identify, right? Clearly, this is critically important. So we've already established that in the first one, the sulfur was oxidized, the chlorine was reduced. In the third, there's no redox on the second one. The third one is redox, but in this case, the sulfur gets reduced, the hydrogen gets oxidized. What happens here? So if you dissect it, you're going to realize that you're going to have 2 Na plus 2 iodides plus Br2, and that gives 2 Na plus 2 bromides plus I2. So what happened to the sodium? Nothing. Nothing happened to the sodium. So when you have a species, and this typically happens with ions, in which nothing happens to them, they are the same before and after, we call these species spectator ions. They're kind of just standing back, hanging out while the others engage in their thing, right? So in reality, this reaction involves iodide reacting with bromine to make bromide and iodine. So the question is, which one is reduced, which one is oxidized? Well, this is a monoatomic ion. Its charge is its oxidation state. So this is -1 oxidation state. Iodine on this side has an oxidation state of 0 because it's elemental iodine. So, because what happened to the oxidation state? Did it increase or decrease? It increased. It went up. Right? So this is the oxidation. Okay? You can actually dissect that further. What happens is that the 2 iodides come together and then 2 electrons are released. And notice, loss of electrons is oxidation. So therefore, by default, we've already established nothing going on with the sodium. This one here has to be the reduction. And we already know that because this has an oxidation state of 0 and it goes down to -1. Yes? If the oxidation state goes down, reduction is what's happening. So what happens to that? Well, the bromine picks up the 2 electrons and produces 2 bromides, right? This is the reduction process. And then if you add these 2 up, well, because these 2 appear on opposite sides, they're going to cancel each other. The true reaction is that iodide reduces bromine. In the process, it becomes iodine, and then 2 bromides result. This is the net redox reaction. Okay? Notice how the total number of electrons lost by oxidation matches the total number of electrons gained by reduction, and it has to be the case. If you're faced with a reaction in which the ones that are lost is not the same, you have 2 here and 3 there, or some other random difference, then you have to technically multiply the reactions by one factor and by another such that the total number of electrons become the same, and then when you add them up, we're not going to do that in this course, but just FYI. All right, so this is a redox process. The species that becomes oxidized is iodide, iodide with a D. The species that becomes reduced is bromine with an N. The element, bromine, is reduced. Okay? All right. The number 5, 1, 2, 3, 4, 5. Number 5 with zinc and everything else. Everybody's good with this? Yes? All right. So what happens in 5, or E? Is that redox or non-redox? It's redox because elemental zinc, elemental copper, right? So what's oxidized? Just by a quick inspection. Which one? Zinc metal, zinc 0, is the one that is oxidized, and in doing so becomes zinc 2+, right? So again, if you dissect this, you have the element of zinc, and then copper 2 chloride is copper 2 and chloride, and then that becomes zinc 2 plus chloride. Oops. And then you have metallic copper, right? You can put a little 0 here because it's a metallic element. So, to which element does nothing happen? So chlorine in the form of chloride, right? So this and this, right? This is a spectator, right? So nothing happens to the chloride. So the true reaction is between the two metals, right? Well, between the metal and the ion of the other metal, right? So the real reaction is zinc 0 becoming zinc 2 plus 2 electrons. This is the oxidation. And then copper 2 picks up those 2 electrons and becomes copper metal. This is the reduction, right? If you add them up, zinc plus copper 2 produces zinc 2 plus copper. Okay? This is the net reaction. So here, again, you can identify this is the oxidation, and this one here is the reduction. Okay? Yes? All right. The last one. So this one is actually, technically you can't classify this one under, you can, but it's, to get to that point, it's more, there's actually things that are not shown on here. It's more complicated to classify for the alternative method that we've been talking about, the 5 categories. But we can at least establish whether it's redox or not. So is it redox or non-redox? It's redox because? The reason is? We have a formation of pure elemental chlorine. So just the appearance of that one pure element, it automatically makes it a redox transformation. The question is, what is reduced and what is oxidized? So if you look at the structures, at the formulas of the compounds, for this one we have to use the method of simply assigning oxidation states based on electronegativity. So for CrO3, what's the oxidation state on oxygen? So how do we establish that? So what's more electronegative, chromium or oxygen? Where by default, nonmetals are more electronegative than metals, right? So this is a transition metal, right? So this is going to be the more electronegative element. So this is -2, right? Oxidation state. Now, how do we establish the oxidation state of chromium? Well, again, chromium plus the oxidation states of the oxygens, of which there's 3, times -2, that has to equal the net charge on the structure, which is 0, right? So therefore, chromium is +6. Interestingly, for charges, we put the number first and the charge after. So we would say 2+. But for this is the rules. For oxidation states, it's +2, +6. The plus or minus goes first. It's kind of to distinguish between one and the other so that people know what you're talking about. So when I write here -2, it's referring to the oxidation state of the oxygen. So this is +6, right? This is +6. So chromium 6. You may have heard of hexavalent chromium. The entire premise of the movie for which Julie Roberts won an Oscar, her only Oscar, I think, is, anybody? Any movie fans in the room? No? So if you haven't seen Erin Brockovich, you should. Very good movie. And it was all about contamination of water supplies in some town somewhere with hexavalent chromium compounds. This is one amongst many. Anyway, so chromium plus 6. Chloride on the left, meaning chlorine is -1 on the left, and on the right, 0. So there you have the oxidation or the reduction. So chloride goes from there to here. So from negative to 0. The number goes up. So this is the oxidation, right? This is the oxidation reaction. It goes from being negative to becoming 0, right? The number goes up. So now we have to go fishing for the reduction. What was reduced, right? So let's look at hydrogen. Hydrogen is +1 on the left, because that's all we have, H+, right? On the right, we have H2O. So the hydrogen is part of the H2O, right? And we've already established, if we look at H2O, this is -2, this is +1, this is +1. So hydrogen did not change either. So what's left? It's the chromium. Because if you look on the right, chromium is 3, right? So chromium went from being +6 to being 3+ charge, which is +3 oxidation state, because it's a monatomic ion. So that's the reduction. It went from a higher number to a lower number. This is the reduction, right? So chromium 6 went to chromium 3, chloride went to chlorine. This is the oxidation, this is the reduction. Nothing happened to the oxygen, nothing happened to the hydrogen. Everybody's with me? All right. Okay. I think we've pretty much said everything that's on this slide. Let me just see what this is about. Oh yeah, this is what we said. The oxidation states can be easily determined with knowledge of the compound's Lewis structure, right? And we've already established that if you draw the Lewis structure and you divide them to give it to the more electronegative element completely, that allows you to determine oxidation state. If you divide the bonding electrons equally, what you're actually calculating is forward charge. We've already been through this, so I don't need to say any more about that, right? All right. Now, there's an alternative method, which in fact is going to turn out to be one of the most important ones that you need to follow. This method that we've been doing is largely for inorganic substances. When you're following organic materials, which is what's going to end up happening when we start talking about biochemistry, then there's an alternative method for following oxidation reduction in organic compounds, which relates to the oxygen and hydrogen content of the structures. So in an organic compound, whenever there's a gain of numbers or bonds to or a combination of the two to oxygen, so increase in numbers of oxygens or increase in number of bonds to oxygen. What's that flying in front of me? Anyway. That kind of distracted me there for a moment. Gain of numbers or gain of bonds to oxygen. In fact, the term oxidation comes from reaction with oxygen. That's because it's a historical term. So whenever there's more, you see more oxygen or more bonds to oxygen, that's an oxidation process. The converse would be less numbers of hydrogens. That also is oxidation. Reduction then will be the exact opposite of that, because they go in the opposite direction. So reduction is less oxygens, less bonds to oxygen, and or gain in the numbers of hydrogens in the structure. So if you pay attention to all those compounds that are listed or displayed there in the middle, on the very left, carbon is bonded exclusively to hydrogen. On the very far right, carbon is bonded exclusively to oxygen and making 2 double bonds to oxygen. So the left side is the most reduced form of carbon. Notice, to make methanol, what has happened? You've made now a new bond to oxygen. So you've gained oxygen, right? It has inserted itself between this CH bond. So this is an oxidation process because oxygen has been gained. If you compare methanol to formaldehyde, what happened? You made from a single to a double bond. So you made an additional bond to oxygen and you also lost hydrogen, right? Because notice this has 4 total hydrogens in the structure. There's only 2 over here, right? So not only did you make more bonds to oxygen, you also lost hydrogen. Those 2 things combined, they can be independent of each other, but together it's oxidation and more oxidation, right? Notice here from formaldehyde to formic acid, all that happened is we gained an oxygen. Hydrogen content has not changed, but the gain of an additional oxygen automatically makes it an oxidation process. And then here we've completely lost the hydrogens. Now the oxygen content hasn't changed, but we've lost hydrogen and we gained an additional bond between carbon and oxygen, right? So that combined is oxidation. So the highest oxidation state of carbon is CO2, it turns out. The lowest oxidation state of carbon is when it's entirely bonded to hydrogen and nothing else. Okay? Now, of course, you can follow the other rule that I showed you, and because I don't have a pen, I can't do it. I'll do it with the 2 extremes, and I'll leave the other. Your textbook has it, so you can look at it in the book. If you do it by the alternative method of because here we've done it qualitatively. Notice we haven't assigned oxidation numbers. We've only done it going by the definition. Lots of hydrogen, more reduced. Lots of oxygen, more oxidized. But we haven't assigned numbers. Well, you can actually do it, right? What would be the oxidation state of carbon over here? So then the question is, what's more electronegative, carbon or hydrogen? Carbon, right? So you give all of these electrons to the carbon, and then you assign. It starts with how many? How many valence electrons does carbon have? 4, right? And it ends up with 8. So this is a -4 oxidation state. Yes? If you go all the way to the far right to CO2, more electronegative is oxygen, right? So you end up like this. Carbon starts with 4, ends up with 0. It's +4. So notice, the lowest oxidation state the carbon can attain is -4. The highest it can attain is +4. And as you go through the motions, it's going to be -2, it's going to be 0, it's going to be +2, and it ultimately becomes +4 as you start losing hydrogens and gaining oxygens. I'll leave that one as an exercise. And it's actually, in your textbook, it's actually dissected in that fashion. Okay? All right. So, just as a sort of a prelude or a preview to the biochemistry concepts that we're going to see later, in biological systems, so let me just mention here, for example, this one here, the zinc with the copper 2, this does not require any enzymes or any catalyst or anything to intervene. If you have a solution of copper 2 sulfate, copper 2 whatever, right? Copper 2 chloride, which is what this one was. And you just add a little piece of metallic zinc, and you walk away, ultimately the zinc will be completely consumed, and in its place, metallic copper will appear. You don't need to do anything. Okay? But in biology, because things are much more complex than just throwing a little piece of zinc to some copper, it turns out that pretty much every reaction, including redox transformations, which are amongst the most important categories of biological reactions, we need the assistance of entities that actually orchestrate, organize, facilitate every single transformation that's going to happen in the human body, because without these entities that we call enzymes, which turn out to be proteins, as we're going to see later, nothing would happen. Things would be too slow, randomness is chaos. Everything needs to be organized. So enzymes provide a very organized microenvironment where things happen in a very orchestrated way, and therefore the speed at which things happen is much more efficient, much faster. than if things were just happening at random. Okay? So, as we're going to see, enzymes also have a very important function of controlling the relative three-dimensional orientation in which things approach each other, which, as we're going to see a little bit later, has important consequences on the ultimate three-dimensional shapes of the compounds that result. Okay? So, the manner in which enzymes orchestrate redox transformations, because you don't want the enzyme itself to become changed in the redox process, they themselves are not the entities becoming oxidized or reduced. They are carrying accessory molecules within their confines that are the ones that serve the purpose of becoming either reduced or oxidized as the other substance is becoming oxidized or reduced. These substances are known as coenzymes. So they're pieces, they're like additional components that an enzyme will carry, if that enzyme is meant to be a redox enzyme, that will then directly participate under the auspices of the enzyme, will then be the one that's oxidized or reduced. So we need to introduce some terminology that just by looking at it should be obvious of what they mean, but we'll describe it. So an oxidizing agent, as the term suggests, causes the oxidation of something else. Okay? Now, of course, if that substance causes the other one to be oxidized, what happens to it? It has to be reduced. Because as we've said, when something's oxidized, something else needs to be reduced, right? So if the oxidizing agent is causing the oxidation of something else, well, guess what? That's the one that's getting reduced. You can also speak of the reducing agent. Turns out both will always be present in the reaction, because it's depending on the perspective that you're looking at it. But you can speak of a reducing agent as the substance that causes the reduction of another. Well, again, if that's causing the reduction of something else, what's happening to it? It's becoming oxidized in the process, right? Because that's it, right? So if you look at this reaction over here, the one that we talked about, the zinc, right? Which is the reducing agent? Well, the one that causes the reduction of the other. So what gets reduced? Well, the copper 2 gets reduced. So it must have been reduced by the zinc. So the zinc is the reducing agent that caused the reduction of the copper 2. Right? Well, if you look at it from the opposite perspective, copper 2 is the oxidizing agent that caused the zinc metal to become oxidized, and therefore it takes the electrons that becomes reduced in the process. Right? So again, it's just a matter of perspective, but both terms are used because depending on the reaction, depending on what you're focusing your attention to, if you're looking at the reaction in terms of an oxidation process, then you're looking at what is the oxidizing agent that caused that oxidation, right? Even though that substance that became oxidized technically is the reducing agent for the other one, but it depends on how you're looking at it. So certain reactions, we look at them from the perspective of oxidation, and then we identify what's the oxidizing agent. Other reactions, we look at it from the perspective of reduction, and then we try to find what's the reducing agent, what's causing the reduction of this, right? And then we go find it, right? All right, so because this is an exceedingly long discussion, we're going to stop there. Oh, no. Oh, I want to see you twice, right? Yeah, it's fine.
And for lab. So for the lab, do you want it to be
long as it's bound that you can't tear things out,
Yeah.
that's
Oh,
fine.
you can.
No,
Oh, don't, yeah.
one that's bound that you cannot.
Yeah, okay, that's fine.
I mean, some people buy, those are more expensive, I'm not expecting that. Some people buy the one that have the carbon copy. I'm not collecting that, those are when you're